All right, let's see how fast we can get this done here. The topic of today's lecture in this chapter is the rates of chemical reactions. Chemical reactions occur at a speed just like we drive our car. Chemical kinetics is the area of chemistry concerned with the rates of chemical reactions. Not only is it concerned with the rates of chemical reactions, but it's concerned with the sequence of steps by which chemical reactions occur. More on that later. Right now we're focusing just on the rate part. The reaction rate is either the increase in concentration of products per unit time or the decrease in the concentration of reactants per unit of time. Rate for chemistry is concentration change divided by time. Your units of reaction rate, what's our go-to unit of concentration in chemistry? Molarity, right? So your rate is usually molarity divided by time, usually in seconds. So it's usually molarity per second or molarity per minute, or when we're dealing with some reactions, even molarity per year. But generally it's molarity per second. This, if you're confused by this, just think of, we do speed in miles per hour, right? As we said on this last slide, when we measure a speed of a chemical reaction, it's going to be different depending on whether we're talking about a product or whether we're talking about a reactant. Not only that, but even more complex, different products and different reactants in a chemical reaction will have different rates of reaction. For example, let's take a look at this chemical reaction right here. As the chemical reaction progresses, the amount of reactant we have, dinitrogen pentoxide, decreases. The amount of product we have, nitrogen dioxide and oxygen, increases. Does the amount of nitrogen dioxide and the amount of oxygen increase at the same rate? No. Look at after 700 seconds. There's significantly more nitrogen dioxide than there is oxygen. So when we're talking rate of reaction, it's a very relative thing. Not only that, but there are several ways we can measure rates of reactions to make the discussion even more interesting. Let's define what some of those reaction rates are. Well, first of all, let's take a quick look at this graph here. We've got concentration on this axis, we have time on this axis, and then we have three different lines, one for each one of our three substances. Our dinitrogen pentoxide decreases during the course of this reaction. So it's the downward going line. Our nitrogen dioxide increases and our oxygen also increases. One thing I would point out is if we were plotting distance versus time for a car traveling at a constant rate, we'd see a straight line where the slope was equal to the speed that our car was traveling. When we look at this graph here, do we see any straight lines? Let me blow it up again. Do you see any straight lines here? Are any of these lines straight? No. None of these lines are straight. So is the rate of the reaction constant? No, it's not. One of the things that makes chemistry so much more interesting than cars is that for several reactions, the rate of reaction for a reaction is not constant. It's going to vary with both time and concentration. It's the equivalent of, to relate it to a car again, sometimes you're driving your car at 20 miles an hour, but you're not always at 20 miles an hour, right? You accelerate up to 20 miles an hour, and then you may have to speed all the way up to 60, and then you may slow down again. Your chemical reaction's rate of reaction is not a constant thing. Therefore, when we talk about reaction rate, we have to come up with a couple definitions and a couple different ways of defining what we mean when we say reaction rate. The first way we're going to define reaction rate is to talk about the average rate of reaction. The average rate of reaction is the rate of reaction over a set period of time. Basically, what you're going to do, and you can ignore the gobbledygook there, basically what you're going to do is you're going to look at your graph and you're going to say, I'm going to take a small period of time and I'm going to assume that the rate of reaction is constant over that small period of time, or at least very close to constant over that small period of time. And I'm going to treat it like it's linear. For example, in this graph here, I'm going to say that I'm going to find the average rate of reaction between 300 and 400 seconds. So I'm going to pretend that between 300 and 400 seconds, that my rate of reaction is constant during that time period, and that my curve is kind of linear. And I'm going to find the slope for that small period of time. So, my average rate of reaction between 300 and 400 seconds would be the change in concentration of nitrogen dioxide divided by the change in time, if I was doing it for nitrogen dioxide. So let's see, I'm doing it between 300 and 400 seconds. So I come down here to my data table because I don't want to have to give myself eye strain trying to read that little graph there. At 400 seconds, my concentration of nitrogen dioxide is 0.0197 minus 300, 0.0160, divided by 400 minus 300, and that gives me 0.0037 molar divided by 100 seconds, or a rate of reaction of 3.7 times 10 to the negative fifth molars per second for my rate of reaction of nitrogen dioxide. Let's write that down. Let's write that down somewhere, and then we're going to make another observation here. All right, let's do this again real quickly, but this time, instead of doing it for my nitrogen dioxide, let's do it for my dinitrogen pentoxide. Once again, it's going to be my change in concentration. At 400, my dinitrogen pentoxide is 0.010, and at 300, it's 0.0120. I'm getting that off my chart here. And my change in time is 400 minus 300. What is my rate of reaction? Well, let's see here. Got 0.0019 negative over molarity over 100 seconds. So that's going to give me a negative 1.9 times 10 to the negative fifth molarity per second. Why is my rate of reaction negative for dinitrogen pentoxide? If we look at our reaction, whoops, I'm zooming on the wrong thing. All right, enough. Okay, fine. You're going to do that to me? Fine. Go over there. Remember, our reaction is the decomposition of this dinitrogen pentoxide. It's our reactant, and you'd expect the concentration of reactant to decrease over time. Therefore, its rate of reaction is going to be negative. Another thing we want to observe is the rate of reaction for this was 1.9 times 10 to the negative fifth. What was our rate of reaction for this? Our rate of reaction for this that we wrote down was, darn it, stop that, was 3.7 times 10 to the negative fifth. So not only do they have opposite signs, but is their rate the same? No. Why is that? Well, for every 2 moles of this I'm consuming, I'm producing 4 moles of this. So you would expect this to be produced twice as fast as this is consumed. And if we look at their rates, that's exactly what we see. 1.9 times 2 is roughly 3.8 times 10 to the negative fifth. So there's a complex relationship, or not too complex a relationship, but there's a stoichiometric relationship between the rates of reactions for different substances. Now is a good time for you to write down Barry Allen. Why don't you write down Barry Allen? B-A-R-R-Y-A-L-L-E-N. Barry Allen. In addition to calculating the average rate of reaction, we can also calculate what's known as the instantaneous rate of reaction. The instantaneous reaction is the rate of reaction at exactly 1 point in time. This is a very specific rate of reaction for just one period in time. Exactly, in other words, we want to know the rate of reaction at exactly 300 seconds or exactly 400 seconds. We want to know what that rate of reaction is. To do that, you take the slope of the tangent line. To figure out instantaneous rate, take the slope of the tangent line. Anybody remember what a tangent line is? A tangent line is a line that touches a curve in just one point. So if I wanted to figure out the rate at just that point that I circled, I'd come up here and I'd draw a line that touched my curve at just one point, and I'd take the slope of that line. It's occurred to me another thing. Throughout this lecture so far, I've been using staple bracket notation. Whenever you see staple brackets in chemistry, that's chemical shorthand for concentration in molarity. So when I say staple brackets oxygen, I'm saying the concentration of oxygen in molarity. To be able to look at a chemical reaction and relate the rates of the different substances to each other. To do this, let's take a look at a really simple example. One cow enters a slaughterhouse, and out comes 3 steaks and 4 burgers. Who is moving faster? Cows or steaks? Steaks. I'm producing steaks 3 times as fast as I'm processing cows. If I was to write this in terms of a delta equation, I would say that my change in steak concentration per unit of time is 3 times the change in my cow population per unit of time. But I'm not even done there, right? Because my amount of steak increases over time and my amount of cows decreases over time. So I have to account for that. So I'm going to put the negative there. So it would be a negative 3 times the rate of my cow consumption would equal my steak production. Why did I put the negative in front of my cows? By convention, we like to think of speed as being positive. So I generally put the negative in front of the quantity that was going to be negative to make it a positive. And you'll find that convention repeated often. Another way of doing it, it would be equally correct to say 1/3 the change of my steak is equal to the opposite of my changing time of cow. Your book recommends that your default mode for relationships is to take the inverse of the coefficient and multiply it by that change. In other words, if I want to relate the production of steak and the production of burgers without thinking about it, I can say my coefficient for steaks is 3. So 1/3, make it my inverse, times my change in steak is equal to 1/4. I have a 4 there, so I change it into a fraction. My change in burger production over my change in time. And that's an easy way to always be able to take the relationship, is to take whatever you have here Actually, let's do that adult style, shall we? Take your coefficients, multiplicative inverse, and multiply it by the change in concentration. And that will always give you the relationship. All right, let's bring this into the world of chemical equations now. Here's a formalization of that rule we talked about with the coefficients. If I'm wanting to relate the rates of all these substances to each other, I take the coefficient, baby A, take its inverse, and multiply it by the change in concentration. B inverse multiplying concentration. Also notice that to make this rate equation work, we also always say that the rate of reactants is negative, because that makes by saying that, putting that negative sign there, negative times negative is a positive, so that makes their rate positive, and that we're relating positive to positive. And we saw on the graph how their concentration is decreasing, so they're by default negative. Let's take a look at our generic chemical reaction there that we were looking at earlier, where we had All right, so we have our generic chemical reaction we've been looking at here. If I wanted to relate the rates of all the products and the reactants together, I'm going to write their individual rate equations. I shouldn't use the term rate equation. That means something else. I write their individual rates here, symbolically. And now what I'm going to do is to relate them, I'm going to take their coefficients and change them into fractions. So I have a 2 here, so I'm going to multiply the rate of dinitrogen pentoxide by 1/2. I have a 4 here, so I'm going to multiply my nitrogen dioxide by 1/4. I have a 1 here, so I'm going to multiply my oxygen by a 1. Then for my reactants, I'm going to add a negative sign because their rate's decreasing. So now I've related all my products and reactants to each other. Chemistry is easy, life is hard, yes? You can use stoichiometry to determine the relationship between the rates of reactions of the various substances in a chemical equation. Let's write the rate of formation of ethanol in relation to the consumption of glucose. First of all, who's going to go faster? My glucose or my ethanol? For every 1 molecule of glucose that's decomposed, I'm going to form 2 molecules of ethanol. So my ethanol is going to form at a much, much faster rate. Matter of fact, my ethanol is going to form twice as fast. Okay, so that gives us the basis of our relationship. My ethanol is twice as fast as my change in temperature. As my change. All right, pause me and try this on your own. Okay, did you pause me? Now they're asking which of these expressions corresponding to the reaction of bromine with formic acid is incorrect. So all of them are correct except for one, or at least I'm going to assume that. Let's start off by cheating a little bit and writing the answers, all our answers on our own here. I'm going to write, well, let's do it one at a time here. The first one says the change in carbon dioxide is equal to the opposite of the change of bromine. All right, are bromine and carbon dioxide on opposite sides of the equation? Yes. And since they're on opposite sides of the equation, there would be a negative sign somewhere in their relationship, so that's good. Are they also both 1-to-1 in coefficients? Yes. So that's correct. Now, and notice how they're using D instead of delta. We'll get to that. Now let's take a look at our bromide ion compared to our hydrogen ion. Well, they're on the same side of the equation, so they'd both be positive. If we were using our default method of writing things, hydrogen has a coefficient of 1/2. Bromide ion has a concentration of 1/2, so we'd write that 1/2 there. Both would be positive. Hey, they've got 1/2, and you can divide out that 1/2, right? If you multiply both sides by 2, those 1/2s would go away. So we're left with a true statement there as well. So that one's correct as well. Now we've come to see where we're looking at our formic acid in relationship to our bromine. They're on the same side of the equation, so their sign's going to be the same whether it's positive or negative. Then they both have a 1-to-1 relationship, so that's correct as well. Next, we look at D here. Change of formic acid is equal to 1/2 that. So let's see. If we were writing it generically, we'd say a negative, because that's a reactant, so a negative change in formic acid per unit of time is equal to, and we come over here for hydrogen, it's got a 2 there, so we definitely put the 1/2 times the change in the concentration of hydrogen. So this is, look what we wrote. What's missing from this expression right here? The negative sign, right? This is a product, so it's increasing. This is a reactant, so it's decreasing, so they have to have a negative sign there. So they messed up. That's the wrong one. If we come over here and look at our last one, our E choice there. If we were to write those by default, we'd say and it has a 2 there, so we'd say 1/2. Then if we were looking at our bromine, it's a reactant, so we'd put a negative there. So that would be the default way that we'd write that relationship. However, if we multiply both sides by 2, that goes to 1, and that becomes a 2. So that relationship's correct. Chemistry's easy, life is hard, yes? Why don't you write down Wally West? Write down Wally West. W-A-L-L-Y-W-E-S-T. Wally West. Now we said that rate of reaction varies with time and concentration. What we're going to do now is we're going to relate the rate of reaction to concentration. One way we can do this is to write a rate equation. This is a rate equation, also known as a rate law. In a rate law, you have the rate equal to a constant, and this constant is known as the rate constant, and I've never seen a book use anything other than a lowercase k for it. So rate is equal to a rate constant times the concentration of a reactant to the m power times the concentration of a reactant to the n power. Quick note, there's a coefficient of a, of little a. Did I use that as the exponent? No. There's a coefficient of n for b. There's a coefficient of little b for b. And I raised b to the n power. Did I raise b to the little b power? No. These powers right here are not necessarily related to the coefficient. So in a rate law, we're writing the rate of a reaction as the function of a concentration of the concentration of the reactants. Because M and N here are not related to A and B, you cannot look at a chemical equation and determine the rate law. You cannot look at the chemical equation and determine the rate law. You have to determine them experimentally. They can only be determined experimentally. Fortunately, that's easy to do. We'll do it in lab. We will also take a look at some data right here in lecture. Let's keep moving. The reaction order with respect to a specific reactant is the exponent of that species of law. In other words, I would say that the reaction is mth order in reactant A. The overall order for a reaction is the sum of the coefficients. So the overall reaction order would be m plus n. And it's alphabet soup. Let's get to some real reactions. Here are some rate laws that have been determined experimentally. Let's zoom in on an old friend here. And this is the reaction that we had. Oh, it's not an old friend. We've not seen this reaction before. But let's zoom in on this reaction right here. An experiment was carried out. Its rate law was found to be as shown here. Notice that there's a coefficient of 5 in front of bromide. Is the exponent over here 5? No, it's not, because this rate law was determined experimentally. Now, if we want to talk order, we would say that this reaction is first order in bromate. We would say that the reaction is first order, because they have an exponent of 1, in bromide. We would say the reaction is second order in the hydrogen ion. Overall, we'd add them together. 1 plus 1 plus 1 is 2, so overall, the reaction is fourth order. Why? Because when we added up our exponents, 1 plus 1 plus 2 is 4. Chemistry is easy, life is hard, yes? If we looked at another example here, we have the reaction of nitrogen monoxide and oxygen to yield nitrogen dioxide. The rate law, experimentally determined, was found to be a rate constant times the concentration of nitrogen monoxide squared times oxygen. Just coincidence that those are equal. We would say that the reaction is second order in nitrogen monoxide and first order of oxygen, or third order overall. Now, the great thing about rate laws is that rate constant has whatever unit is necessary to make the rate of reaction equal to units of molarity divided by time. At the very beginning of this, we said that rate has units of change of molarity over time. So your K, or your rate constant, is going to have whatever units it takes to make that happen. For example, if I have a rate law that's second order, right? I have a squared what are my units of K going to be? Well, I know my rate has to have units of molarity per second. I know that whenever I see those staple brackets, that's chemical shorthand for molarity, so I know I have molarity squared. So my K would be molarity per second divided by molarity squared, or another way of writing inverse is to the -1 power, right? Those are the same units. So K is going to have whatever units it takes to make the rate of reaction coming out as molarity per second or molarity per minute. So if it's first order, your rate constant is going to be inverse seconds. Second order, what we just solved for. Third order, that, and you'll very rarely have a reaction above third order, and we'll talk about why that is later. But a third order would even be an extreme reaction. Most reactions are either second or first order. This is a very common test question, by the way, on national exams and on your test bank, is they'll give you a reaction and they'll want to know what the units of the rate constant are. They won't ask you anything else, they'll just ask you the units of the rate constant. Alright, gold catalyzed decomposition of hydrogen iodide into its elements was determined under high pressure conditions to be 0th order. What are the units of the rate constant for a 0 order reaction? Alright, let's write what the rate law for a 0 order reaction might look like. It would equal rate times K times the concentration of hydrogen iodide to the 0 power. Anything raised to the 0 power is 1. So for a 0 order reaction, our rate law is rate equals a constant. In other words, we're operating at a constant rate. So if it comes to putting units to that, we know our rate is always in molarity per second, and K has whatever unit it takes to make that happen. Well, rate equals K, so rate K must equal units of molarity per second, or D, right? Because whenever you're dividing by something, it's raised to the -1 power. They do that a lot in kinetics. Use that -1. Consider the following rate law expression. Rate is equal to a constant times the concentration of A times the concentration of B. Which of the following is not true about the reaction having this expression? The reaction is first order in B. Yes, whenever there's no exponent shown, it's 1. The reaction is second order overall. Well, it's first order in B and first order in A, and 1 plus 1 is 2. So that's correct. The reaction is first order in A, yes. Doubling the concentration of A and B doubles the rate. All right, well, let's see what happens. Let's do the algebra on that. Rate is equal to a constant times the concentration of A. So I'm doubling the concentration of A times the concentration of B, and I've decided I'm doubling the concentration of B. So that means 4K A B. So did my rate increase by 2? No, it increased by 4. So it quadrupled. And I can't spell quadrupled. So that one is not true. Which by actually, if you think about it, that makes none of the above not true as well. Bum, bum, bum. The method of initial rates is how we determine the rate law in the laboratory. Let's take a look, or one of the ways. To show you how easy it is to determine rate in the laboratory, let's take a look at this scenario. Studies were performed on the following reaction. In one set of experiments, when the concentration of bromate was halved, the rate was also halved. In a second experiment, the concentration of bromine was doubled, and the rate was doubled. In the third experiment, the concentration of the hydrogen ion was increased by a factor of 3, and the rate law was found to increase by a factor of 9. What is the rate law? We got a lot of information. What we're going to want to do is we're going to want to break it down to one set at a time. So let's deal, first of all, with just the bromate. They said that the concentration of bromate was halved, and that the rate was also halved. So what they said is we have bromate to the n power times a constant equals a rate. and that when I halved my concentration of bromate, my rate was halved. What can I raise n to? What power can I raise 1/2 to get 1/2? 1, right? One is the only way to make this a true statement. So my rate law has to have bromate as a first order. So I can go through my choices here, and anything that doesn't have bromate as a first order I can cross out. So I can cross that out since it has bromate to a 1/2 power. So that's gone. Next, let's look. In a second experiment, the bromide concentration was doubled and the rate doubled. All right, so I have, did I say bromate? Bromide. So I have bromide to the m power equals rate. I double my bromide concentration and my rate doubles. What value of m here would make this a true statement? Once again, 1's the only value that would make that a valid statement. So I know my concentration, so I know my order of bromide has to be 1 as well. So anything that doesn't have bromide as first order we can cross out here. That's 5th order for bromide, so we can cross that out. That's first order, that's first order, that's first order, so we're still in the ball game here. Next, let's take a look at our hydrogen ion concentration. That's the only thing we've got left. Whoops, things that I crossed out disappeared. In a third experiment, the concentration of my hydrogen ion was increased by a factor of 3. The rate was found to increase by a factor of 9. So I have my hydrogen ion to the x power equals a rate. When I increase my hydrogen ion concentration by a factor of 3, my rate increases by a factor of 9. What value of x would make this a true statement? That would be a true statement when x is equal to 2, right? Because 3 squared equals 9. So that means that my hydrogen ion is second order. So anything that doesn't have hydrogen second order I can cross out. So my rate is equal to a constant times the concentration of bromate times the concentration of bromide times the hydrogen ion concentration squared. That last example was basically a simplified look at what we're doing with the method of initial rates. In the method of initial rates, you take a reaction and you perform that reaction several times. However, what you're doing is you're carefully controlling the initial concentrations of each of your reactions, each of your reactants, hence the term initial rates. You start off and you control your reactant concentrations so that you're keeping all but one of your reactants constant. The other reactant, you're changing its concentration. And you're seeing how the rate responds to that change in concentration. For example, we have the reaction of nitrogen monoxide and oxygen to yield nitrogen dioxide. And here's some lab data from the method of initial rates used on this experiment. All methods of initial rates work on the algebra trick of dividing out equations. Let's take a look, examining our first two experiments. In experiment 1, and I need to start over here if I'm going to get more room. In our experiment here, the rate of experiment 1 is equal to a constant times the concentration of nitrogen monoxide to the m power times the concentration of oxygen in experiment 1 to the n power. If we plugged in actual numbers, we'd have I'm pulling these numbers off the chart there where I circled them. And then the other side's that rate there, right? So that's all for experiment 1. What we're going to do is we're going to divide experiment 1 by experiment 2. And I'm going to divide both sides of my equation by it. So I'm going to divide the rate of experiment 1 by the rate of experiment 2. And I'm going to divide the other side of the equation that way too. I'm going to divide by the rate constant times the concentration of nitrogen monoxide in experiment 2 to the n power. And remember, these experiments have been designed so that the concentration of one of the reactants varies and the others are held constant. So when I plug in my data for experiment 2, that's a 3 there. Equals, and I'm going to divide the rates by each other, 0.192 moles per second. So I just pull those numbers off my chart, and I'm basically dividing two equations by each other. So I set up the rate law using the data from experiment 1, and then I divided it by the rate law from experiment 2. So I took the data for experiment 2 and divided it. If we look right off the bat, we can see that we don't need to know the value of n. Why? Because 0.15 to the n power is going to be the same as 0.15 to the n power. And anything divided by itself is 1. The same for our constant. So our constant's going to 1 when we do that. So that leaves us with a simplified expression of 0.015 divided by, and because multiplication is commutative, we can go 0.015, 0.30. We can do the division, then raise to the m power. So I'm combining these two terms right there is what I'm doing. Now let's actually reach for our calculators and do some math here. Well, I don't need my calculator. I take it back for that first side there. And my guess is 0.048 divided by 0.192 is I get 0.25. When I divide this out, I get 0.52. So what can I raise the m power to get 0.52? Couple things that will help is you have to be able to recognize magic fractions, right? 0.5 is 1/2. 0.25 is a quarter. You really need to be able to recognize those magic fractions. We talked about them some last semester. But at any rate, if you can't look at that and solve for m, like most of you are saying, well, m's equal to 2 there, because if we translate 0.25 into a fraction, got m, right, 0.25 is the same thing as a fourth, and what's going to equal 1/2 to what power is a fourth? It's squared, right? 1/2 squared is a fourth. All right, let's say you can't look at it and recognize that relationship. Let's say you were totally lost. Oh, gee whiz, I'm lost, Dr. Kelly. I don't know how to solve for the m value. I don't recognize any of these decimal places. What can I do? Here's what you do. Let's change our fraction into a decimal. So we have 0.5 to the m power equals 0.25, and we don't recognize what the value of m is. What you're going to do is you're going to take the log of both sides. By taking the log of both sides, that lets you pull the m down. So you have m times the log of 0.5 equals the log of 0.25. So m is the log of 0.25 divided by the log of 0.5, and when you punch that into your calculator, it gives you 2. So m is equal to 2. So if we go back up to our rate equation now, we now have the value for m. We now know that m is 2. Alright, so how are we going to find k and how are we going to find n? To find n, we're going to repeat the exact same process that we did last time. However, this time, we're going to have to choose two different equations. We want to choose two experiments such that our nitrogen monoxide cancels out this time. Alright, so we look for two experiments where the concentration of nitrogen monoxide is constant. And we actually have two different options here. I could choose experiments 4 and experiment 2, or if I wanted to, I could choose experiment 3 and experiment 1. Either one will get the job done. Let's do 2 and 4. So I'm going to say the rate of experiment 2 and that's a 3. I swear you can't write 3s with a stylus. And we're going to divide everything by experiment 4. Alrighty then. Now it's math time. Math time. Alright. Any number divided by itself is 1. So that simplifies us to 0.015. Hey, they like these concentrations apparently. To the n power equals 0.192, 0.384. So we grab our calculators again. 0.192 divided by 0.384. Hey, what do you know? So we have 0.5 here, and we have 0.5 here. So n must be 1. So now we know our reaction is first order in oxygen. So if we come up to our rate law here, we now know that the value for n is 1. So we've got a pretty good rate law going here. We've got rate is equal to a constant times nitrogen monoxide's concentration squared times the concentration of oxygen. Solving for K is really easy. All you have to do is choose any one of these experiments, and it doesn't matter which one, and plug and chug. Alright, so now all we have to do is some plugging and chugging. And what we're going to do is we're going to choose one of these. Let's see, have we not used one? I don't think we've used 3 at all. Let's just use 3, just for the heck of it, so that 3 doesn't feel ignored and unloved. And we're going to substitute this data into our rate law. We know that 0.096 is our rate. And let's do our units here as long as we're doing things. Molars per second times the K that we're wanting to solve for times the concentration of nitrogen monoxide, which we now know is squared, times the concentration of oxygen. Whoops. There I go, writing it symbolically. Times the concentration of oxygen, which is 0.030. We do some math, and that gives us 0.015 squared times 0.03 equals K times 6.75 times 10 to the negative 6 molars cubed, right? Because I got molar squared there, times molars is molar cubed. Wow, my handwriting's gone downhill during this. Times 0.96. That's a 96 there, not a 4. Just so you'll know. 96. And that gives you 1.42 times 10. And it looks like we're really at 3 sig figs here. So, I mean 2 sig figs. To the 5th. And we look at our units. That cancels that to a 2. So it would be negative 2 seconds negative 1. So now we can state our rate law, and it's 2 sig figs. So now we could summarize our rate law by saying that our rate is equal to 1.4 times 10 to the 5th times the concentration of nitrogen monoxide squared times the concentration of oxygen. And that's the method of initial rates. Chemistry is easy, life is hard. Why don't you write down J. Garrick? Write down J. Garrick. J-A-Y, and then last name Garrick. G-A-R-R-I-C-K. Here's another way of working with the method of initial rates from a purely conceptual point of view. The relative rates of the reaction A plus 2B yields products are shown in vessels 1 through 4, and their relative rates are 1, 2, 2, 4. The red spheres represent A, the blue spheres represent B. Okay, so this really involves some counting. In my first box, I have 2 A's and I have B4s. Then in my second container, I have A4 and I have B4. In my next container, I have A2, and for my B's, I really should be doing this color-coded, shouldn't I? B4. For my B's, I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8. And for my B's over here, 1, 2, 3, 4, 5, 6, 7, 8. I have 8 as well. And for my A's, I have 1, 2, 3, 4. I have 4. Now, they've told me that the rate of reaction for these comparatively is 1, 2, 2, and 4. It looks like we're not able to do the method of initial rates, but we really are. Our rate law, after all, would simply be rate equals a constant times a to the n power times b to the m power. Let's see. We want to choose an experiment where a is the same, where b is constant, but a is different. If we do that, we can use 1 and 2. In both 1 and 2, b is being held constant, but a is changing. So our rates, I'm going to go 1 to 2. So I've got 1 to 2 is the ratio of my rates. My concentration of A is 2 in the top equation. My concentration of A is 4 in the bottom. And I've got my B's, which are 4 and cancel out. So I have 1/2 equals 1/2, right? Because 2 divided by 4 is 1/2. So in other words, when I doubled my concentration of A, my rate doubled. What value of n would make that statement true? N has to be 1. So the reaction is first order in A. Now let's try it for B. If we try it for B, let's see, we need to hold A constant this time, but change our concentration of B's. So I'm going to choose 2 and 4. So I'm choosing 2 and I'm choosing 4. When I do that, I'm choosing rate 4 divided by rate 2. So I've got 4 divided by 2. My A's cancel out, and I've got 8 divided by 4 to the m power. So that gives me 2 equals 2 to the m power. So m is once again 1 there, it looks like. So that means our reaction is first order in B. So if we were to write our overall rate law, we would say that our overall rate law is rate equals a constant times the concentration of A times the concentration of B, and that we're second order reaction overall. Chemistry's easy, life is hard. What can I say? It's even easy if you're impulsive. Why don't you write down impulse? Write down impulse. I-M-P-U-L-S-E, impulse.